Alright, we're going to keep talking about our eyes here, okay? Talking about our eyes. Remember, your algebra class, when we talked about eyes, to calculate an eye, remember the eye is simply the sum of all of the MR squareds, okay? That's how your algebra teacher taught it. An example of that would be this rod or this meter stick with 3 clamps attached to it. If I have this meter stick just rotating about the axis that is my right hand there, then this rod has a certain resistance to rotation. And all I would do to calculate its I is add up the mass of this C clamp times the distance it is from the axis of rotation, square that number. To that, add the mass of this C clamp times the square of the distance it is from the axis of rotation. And then to that number, add the mass of this C clamp down at the bottom times the square of the radius it is from the axis of rotation up there. And if you want, you could add the center mass and the mass of the rod itself, the stick, and times its length or distance or radius from the axis of rotation. And so this rod, all of that together, just push the plus button, sum of the MR squareds, that would be this rod's I. That's algebra, just sum of the MR squareds. Now in calculus, we'll still deal with rods, but we're not going to have lumpy rods here, okay? We're not going to have a little bit of mass, then a lot, then a little, then a lot, then a little. What we're going to focus on in calculus is uniformly distributed mass of different shapes. So it'll be just like a meter stick with C clamps, but there won't be any C clamps on it. We're going to talk about the eye of just a plain stick. All right. So this stick, uniform distribution of mass, you can call it a stick, call it a rod, doesn't matter. It will behave differently if it rotates around one end. We'll calculate the I for that. That will be very different from the I if it rotates around its center mass. You guys know that. So that is a different I. And we could go anywhere in between those I's. I could have it rotate 1/5 of the way from one end, and you could calculate what its I would be if it's rotating at the 20 centimeter mark, the 25 centimeter mark, 1/4 of the L, it would behave differently, or at the 33 centimeter mark, it'll behave differently. So wherever the bounds are is the only thing that's going to change. It'll stay the same formula, which the calculus version of that formula, the I is, remember in calc, all we do is take a letter S that looks like that and turn it into a letter S that looks like that. All right, so it's going to be an integral. I will write the R squared first and multiply that by a differential mass. So what we're going to do, take this stick, we're going to cut it into 100 centimeter sticks, or we can cut it into 1,000 millimeter sticks, either one, and add up all of those differential masses times the square of however far they are from wherever the 0 mark is, and add them up. That's what an integral means, okay? Now, this should sound pretty darn familiar because we did the exact same thing when we found our centaur, okay? We're going to base this on uniform density, a uniform distribution of mass. So remember, rod is one-dimensional, so instead of using rho for the density, the mass divided by volume, we're going to use lambda for density, mass divided by length. All right, so sometimes they just call it a length density. And remember, since density is uniform, any size piece of rod is going to have the same density. So the mass of the whole rod divided by the length of the whole rod is going to be the exact same thing as a centimeter's worth of rod's mass divided by that centimeter's worth of rod's length. So when we use this, you probably remember, if I solve for a differential mass here, which I would then put in that equation up there, that differential mass is equal to the density, the lambda, times that differential length. Alright, that should again sound familiar because we did this when we found our center, okay? So it's a very similar procedure. So, what if I have a rod, like a meter stick, doesn't matter, it's going to rotate around one end. That dotted line means that's the axis of rotation. I called that the 0 mark of rod. The other end I just called L. So it doesn't matter if rod's a meter stick or if rod is a foot stick or a yard stick. No, it doesn't matter. A rod of any given length, uniform mass distribution. All right. So I just drew rod there. I picked a little sliver of rod. That's going to be that differential mass. You could also refer to it as a differential length. You could add up all of those masses. It would equal the mass whole. You could add up all of those little slivers of length. It'll equal the length whole. Doesn't matter. But we will refer to it as a differential mass because that's what we're going to substitute into the formula. So we're going to add up all of those differential masses from 0 to L. So the bounds of our integration there is from 0 to L. That makes sense. R squared dm. That's the formula I just gave you. That's any given I. I always start with an R squared dm. What I just reminded you, though, is that differential mass is a lambda times the differential length. So all we're going to do is simply substitute where that dm is. I'm going to write lambda dl. So down here, this will be the integral from 0 to L, R squared lambda dl. That's it. All right. Now, out of that R squared lambda and dl, the only thing that doesn't change in this example is the lambda. That lambda stays constant, but the R goes from 0 all the way to L. So that R is what's changing. So I'm going to fish out the lambda. It becomes from 0 to L R squared dl. All right. Now it's set up. All you got to do is the calculus. This is actually pretty easy. All I'm going to do is turn that R squared into the calculus version of the integral of R squared. So that will end up being R to the third over 3. And I will put 0 and L in where the R is. So then I will multiply that quantity by lambda. That will be what I equals. So what you guys know this becomes is lambda times L to the third over 3 minus 0. All right, if you want to put that in now. You remember what we did when we found our centaur? We can replace that lambda because chances are you don't know what the density of a foot stick is or the density of a meter stick or the density of any given rod. But chances are you do or could very easily know rod's mass and rod's length. So remember what we will do is swap out that lambda for what lambda is, the mass divided by the length, the mass whole divided by the length whole. So where that lambda is, I'm going to call it m over L, multiply that by the L to the third over 3, and what we end up with is that becomes a square, right? And what we have is what? 1/3 of the mass whole times the length of rod squared. That is the I of rod if he is rotating around the end of one of his ends. All right, a rod, or so it doesn't matter if it's a meter stick or a foot stick. If rod is doing one of these, his moment of inertia, his resistance to rotation is 1/3 of the mass of rod divided by the length, times the square of the length of rod. It's that simple. Now, what if we change the axis? You guys know if you change the axis, then the I's change, right? If that's the center mass now, let's have that dotted line be the center of rod. So now rod's going to rotate around his center mass like yay. Okay. So I'll do the exact same thing. He's got a differential mass. That's a piece of the differential length. Just change the bounds. The only thing we're going to do is change the bounds. Instead of the bounds being from 0 to L, we're going to go from his center mass to a spot that is negative L over 2, half of the length, to a place that is positive L over 2, the other half of rod's length. That's it. Just go from negative L over 2 to L over 2. So It'll be r squared differential mass. We'll do the exact same substitution. That differential mass is lambda dl. It'll be r squared lambda dl. All right. Now I'm going to write the bounds in the next one. I'm sorry, I didn't quite write it in this one. But I'm going to fish out that constant lambda, and I'm going to have negative L over 2 to L over 2 r squared dl. Now we're ready to do the actual calculus, all right? That r squared becomes an r to the third over 3. So what I did is I just fished out that 3. I put it as a lambda over 3, and I'll scroll up so you can see the rest of it. Now, the L over 2 is cubed. And then I subtract the negative L over 2 that is also cubed, okay? All I did is just fish that out. So it's going to be an L to the third over 8 minus negative L to the third over 8. And that's a negative L being cubed. We end up adding them. So this becomes lambda over 3 times L to the third over 8 plus another L to the third over 8, which becomes, I did. Okay, let me go ahead and finish this up then. So this becomes lambda over 3 times 2L to the third over 8, right? I'm going to call that 1/4. So this will be a lambda over 3 times 1/4 L to the third, okay? Now, remember, what can we do with that lambda? This lambda, I'm going to replace, and I'm going to call it the mass whole over the length whole, and that will be times, what in the denominator now, it'll be 12, and this will be over L to the third, right? So, what does this end up becoming? It ends up becoming 1/12 ml squared, and that is the happy version of the eye of rod rotating about its center mass. So 1/12 is obviously less than 1/3, so it's easier to rotate this way than it is to get to rotate this way. All right? So what if we put the axis anywhere else? Anywhere else, it doesn't matter. You can put the axis wherever you want to or wherever the question then tells you to. Sometimes it'll say, hey, what's the eye of a rod rotating 1/4 from the end, 1/5 from the end, 1/3, whatever. It doesn't matter. Pick a spot. But if they ask you, what is the eye of a rod going from an axis of 1/4 from the end, then this is negative L over 4, and this is positive 3/4 of L, or 3L over 4, however you care to word it. So what this ends up being is set up like this, r squared dm. Always start with that negative L over 4 up to 3L over 4. Those will be your bounds. Do the exact same strategery. Go ahead and try it, because anyone can watch physics. You all have to do it sometime, and it'll be a lesson in why fractions suck. But sometimes the fractions get a little annoyous, but you should end up getting 7/48 ml squared. All right, remember, i's are all y's, some fraction of an mr squared or an ml squared. Sometimes it's just a plain old mr squared. Sometimes it's a 1/2. Sometimes it's a 1/4. Sometimes it's a 1/12. In this case, it'll be 7/48. All right, but those fractions come from the manipulation of the calculus. We're always going to base it on density, having a uniform mass distribution, and that density stays the same whether it's the mass times the length of the whole thing or the mass times the length of a tiny piece of the thing. All right, this one hopefully isn't too tough. Again, remember, it's always based on that formula, r squared dm. It'll always be a rigid object, uniform distribution mass using density. All right, so this one hopefully isn't too terrible. We'll do some more intricate shapes. The next one will be circles. If we take rod and bend them into a circle, now I have a ring. Those differences, instead of going from 0 to L, we're going to still go from 0 to L, but the L will be the length that is a circumference, so it'll be from 0 to 2 pi r. Then we're going to get a ring and make it a solid disc, and I'll show you that. But anyway, that's stuff yet to come, and we're coming up on the end of 15. So hey, yay physics, and let's keep an eye on things